should get started.
Okay. We've got a slightly different group here than we had this morning, so I'll make the point that, apart from the fact my name is Barrie Gilbert, there are quite a few slides, and we'll rush through them a little bit, but you're welcome to have the PowerPoints of both this and this morning's lecture on noise, and as a matter of fact, there's a lot more, but I better not get too gushy. This is about an idea that I think is worth giving some thought to, and we will for an hour or so. I make this rather simple point, that in any creative life, as humans, we only have a very small number of really important ideas, and maybe not even any important ideas, but we generally rely upon a bunch of ideas that we have had since we were young, and we put them in our little polka dot bag and carry them around on our back and dig into them every now and again, polish them up, use them a bit, and put them back for the next time we need something like that. And there aren't very many strongly different ideas that I can figure in my own life. Now, of course, if you think of the greats, well, let's see, Galileo, I guess he invented the cosmos. Newton invented light. Robert Hooke invented springs and things. Shockley invented holes and electrons. How's it go? So, you remember these people because of the big things they did. Of course, the fact is that they led lives just like you and I and had lots of little ideas, but only a few that stuck around. And this idea of using just a few ideas in a lifetime is what I mean by the continuity of concepts. And it just struck me some time ago that there's a particular geometric form that keeps coming up in my life, and it's not the only idea I've had, but this is the idea of a circle. So I'm going to draw on a number of earlier presentations, so there'll be occasionally a little transition where we look like we're starting all over again with a new show, but that's just because it's patched together in that way. You'll see what I mean by this in just a moment, I hope. Let's start with the magnetron. I'm going to talk quite a bit about the magnetron because it happens to be a rather wonderful thing that does an amazing job of transforming raw DC power into microwave power without much help from anything else. It's really a miracle. This, you may put, if anyone wants to speak up, you're welcome to. If you shout out what you recognize this to be, you get points for that. Okay, no points. That's a cyclotron, invented at Berkeley by, not Rutherford, but there's no awful. I've forgotten the guy's name. That's fame for you. Who?
Lawrence?
No. He'll come back a bit. This is another manifestation of the circular theme. In this case, it happens to be a klystron. This I'll talk about a bit. That's a decatron. This is one of my early carrier domain multipliers. Again, the circular theme pops up. This is some character-generated work I did at an early stage of developing a readout system for the Tektronix 7000 stereoscope. This is a carrier domain magnetometer, which I'll tell you about toward the end. And of course, it's worth remembering that the silicon atom, which is at the basis of pretty much all we do, has this circular idea to it, or really strictly spherical idea. And even more strictly, who knows if those really exist as little point particles or not. I don't really care very much, because I can think about billiard balls popping in and out of atoms and becoming available for conduction, so it's fine with me, but it's not fine with a lot of people that we should talk about orbitals in that way. Here's another, it doesn't look very circular just yet, but the idea of being talked about is the idea of a translinear loop, where a loop of junctions is arranged to perform a certain function, and we'll talk ever so briefly about that. So, here's a quote, which isn't the quote I want. Isn't that funny? It's in the wrong place. But anyway, just read it to yourself, and I'll come back and tell you a bit more about who said that but I actually wanted another quote that was a bit more on the money. But anyway, okay. Okay, that slide got out of place. Never mind. That was Carver Mead, of course, who said that. So this was the beginning of another little show that I call Electron Tornadoes, Paper Circuits, and Super Integrated Spinning Tops. Again, though, it's a journey along this idea of a continuum of concepts that one comes to connect with and comes to love and utilize in lots of different ways. I'll just show you briefly sort of my starting place because it actually is more relevant than it may first seem. There's a town there called Bournemouth, that's where I was born, and not very far away there was a little tiny village, there still is a little tiny village, called Worth-for-Travers. You see it there. And Worth-for-Travers was on the map big time in 1937, the year I was born, because it was there that in about a year later, the first samples of the cavity magnetron were posted by Royal Mail from Birmingham University down to Worth-for-Travers at TRE. And if a spy had known about this little brown package, he'd have salivated because it contained two of the original magnetrons invented by Booth and Randall up at the University of Birmingham. So the point I'm making here is that there's a sort of a very visceral connection for me because this was only a few miles from where I lived. I lived in Bournemouth up there, and to get here you travel over the ferry at Sandbanks. There's a Marconi Memorial there where the first transatlantic transmissions were made by Marconi. Then you drive down to Nine Barrow Down and eventually find this little tiny village. And that's just how Google shows it today. It's not very interesting, but that little bump at the bottom is the place we're interested in. That's how it looks. It's just a one-pub village, very dozy place. At the south we have France, of course, over the English Channel, and then, more importantly, during the war years, of course, onward to Germany. So it's pretty easy for German aircraft to fly over to Britain and do naughty things. That's just not a comment. Okay, so this is how that place looked in 1937. It was called the Telecommunications Research Establishment. And as I say, it was there that radar of the kind we would think about today as being particularly perceptive radar, having very narrow angular resolution, first took flight. And the radar at the time was implemented using the system called chain home, which was a series of high towers and transmitters working at UHF frequencies. I'm not really sure quite where, but in the 250 to 450 megahertz range. There's a great book by Robert Barrie called The Invention That Changed the World, all about radar. And it changed my life because of all the things that happened when the war was over. This is Sir Watson Watt's chain home radar, the low frequency stuff. It's sleeping peacefully now in the British Museum, dreaming about the good old days. And I can actually relate very strongly to tubes, vacuum tubes like this. I used those as a kid, and CRTs don't look very healthy, but CRTs of that sort. So the concept really begins in my own life with this idea of a device that really, it really did save Britain from invasion during World War II. It was a big deal, and two samples of the cavity magnetron were brought over to MIT, and then USA got into the magnetron business after that. Now, this is the early magnetron, and it's a little bit hard to see the structure, so I'm going to get rid of some artifacts in the photograph over on the right there. These are two I'm pointing to the wrong place, aren't I? Two semicircular anodes. You remember anodes, I expect, and cathodes, which are surrounding cathode, which is that wire down the middle, and the two anodes are connected to a couple of connections that allow us to do things. So what are the things we're going to try to do? Well, an external resonator was attached to the anodes A and B, and the electrons emanating from the cathode, which normally would just fly radially to the anode under the influence of the E field, are persuaded to also spiral because of the H field which is pointing this way. And under the right conditions of operation, this little tornado shower of electrons could be made to induce our power in that tank circuit. But it was very inefficient for a number of fairly obvious reasons. The fact that the external tank had to be wired to a couple of anodes meant that there were some losses in those connections and so on. And many attempts to make magnetrons like this were made, but they didn't work very well. I've got some of these in my own collection, and I plan to fire them up someday. So let's talk a bit about those tornadoes. This is the Boot and Randall magnetron. I've added a bit of color where the cavities are just to show you roughly. That's about an inch and a half in diameter at that point. The big flanges are where the magnets will attach. This wasn't evacuated permanently. You had to pump it down to use it. It was fairly efficient, surprisingly efficient, but nevertheless in producing, say, 500 watts of RF power at an efficiency of 50%, that's still 500 watts you have to dissipate in cooling. So it was cooled by water at the time. Modern magnetrons are quite a bit more efficient. So that was the thing. I've seen this in the Science Museum in Britain quite recently, and it's just, I would love to have one, but of course, wouldn't we all? So now this is a more modern magnetron, not all that modern. This was used in RAF, in fighter planes of the British Royal Air Force, but it came later. But it's more a more concentrated solution now, because the resonators are built in to the anode. This is a copper block, and these are holes that are milled by high precision machinery, and there are many ways of actually making these cavities, but this is a common form. And then at the center we have a cathode, a means of heating up the cathode, and then an output probe that delivers RF power. There's quite a bit that could be said about exactly how this works, but I think I can give you a fairly good idea this way. So this is my drawing, but this is how that block would, how the transport of current would look in the absence of a magnetic field. It's just a diode, cathode, anode, and that's it. So these electrons would gain a good deal of energy because of the high bias voltage, very negative on the cathode and ground on the anode, and they just lose that energy as heat, and it wouldn't be much fun at all. But with the addition of magnetic field, we can cause this swirling of the electrons. And you can understand, I think, intuitively that there are many modes that this thing might get into. But the mode you wanted to get into is where, as the electrons interact with this whistle, as you like to think about it, this doesn't do anything. No, it doesn't work too well. But you know, you've seen a little whistle you can blow across. It's just electrons blowing across a cavity whistle, and the energy that is becoming embedded in this region of dielectric with metal is coupled back into the electrons as further new electrons come around. So there's an energy back and forth between the cavity and electrons, reinforcing what happens at the next cavity and so on. And under the right conditions of H field and E field, rather surprisingly, this thing just lit up like a million-watt candle. Not quite a million, but it was an amazing achievement for a first try. So, being so close to my home, when after the war a lot of this stuff became available for dirt cheap price, I was obviously one of the kids on the block that bought this stuff. Now, I want you to look at this picture and see a very important detail of it. Can you see it? Oh, come on, your eyesight must be that good. Right there, can't you see that? That's a church. It's a Norman church. I think it's 1100 or something. Pretty old church. There it is, and a rather fuzzy picture of it is right here. I often go down there. It's a 2-mile walk from the main road down a dirt track, or a bridle path it's called. And there's the Norman church, and then there's a Coast Guard station, and there's a memorial to the magnetron there. And how do we come to see that again? Well, never mind. You can see it. There's the path I just talked about. It's a long walk. And there's a little church. No, there's a church, and this is the Coast Guard. So it's perched right on the ocean front. And the reason I show it, it will become apparent in just a moment. That's the memorial. I can't remember what the plaque says, but something like, here a very clever idea was first tried out and it worked. Wasn't that nice? Something like that. So I like to believe that in the middle of the night when everyone is sleeping, this thing wakes up and it begins to do a little dance with St. Albans Church, and they have a lot of fun together, remembering the good old days. But the reason really for being serious about this, if I can be for a moment, is, hello you down there, can I turn the light down a bit? A bit really means off, because that's the only binary chance we have here. But so this was the first target ever used by the magnetron radar working at 3 centimeters that was invented at TRE, 10 miles or so from my home. And they directed their parabolic antenna and magnetron waveguide, magnetron-driven waveguide toward this church, and they got some first reflections from that church. So that's a very historical place for a lot of reasons. I expect the Normans had another reason for saying it was historical. So they do this little jig in the middle of the night when we're not there, because no one else is around there at night. And this is the pub. It's called the Square and Compass, co-signed by the young guys that celebrate over there. And again, in the middle of the night, the lights come on and ghostly figures walk around talking about the good old days. Now, this is a much more modern, well, again, I should say much more modern. This is a modern magnetron, but modern only in the sense of meaning, say, 1940 or 42, something more like 1942. But it made a very quick development into a much more potent form. The efficiency was higher. It was more manufacturable. Of course, you can tell by just looking at that old Booth and Randall magnetron, it was a bit clumsy. And this was permanently evacuated. So there's where the cathode will go, and that's the anode block. And there's a probe. You just like to see the probe that couples into the RF output. And down here, of course, we have the heater connections. So what's remarkable about this is here we have a device that's no more than a diode. That's all it is. It's a diode that can squeal like mad at 10 gigahertz or so. And to this day, it's a wondrous device. I kind of have a hopeful longing that one day we'll be able to make a graphene magnetron. Or to put the emphasis elsewhere, a graphene magnetron. Because I got a feeling it can be done. This is a more modern magnetron. It's the sort of thing you'd find in an oven, but it's not actually from an oven. But you can just see here now that it's cheaply made with welded copper vanes, and the cavity consists of these vanes at an angle. This looks back in toward the cathode, and it's very cheap to make, but nevertheless can be very powerful in spite of the crudeness of those cavities. The fact is we don't have to have a nice circular cavity. There's lots of ways to kill a cat. Oh, I shouldn't say that. I got 4 of them. So after the war, there is the, I thought I put that in there, didn't I? There's the quote. And if you read it and you think about it, it looks like something I might have said. Well, you wouldn't know that, would you? But that's exactly how I got my start. But it wasn't me, and you've already seen the guy's picture. It was Carver. Carver Mead said that. And when I read it first, I thought, man, that's exactly my experience, because you could buy this stuff for pennies. Wonderful stuff. Let me see if I've got something here. Here's one. This is an indicating unit type 73. It has one 3.5-inch CRT. There's a circular theme again. It'll come up many more times than that. And these things worked. They were loaded with interesting stuff. You can't see it in this picture, but I don't know how it looks to you. Up here, those are a whole bunch of adjustment potentiometers that you trim on the other side of the panel. But it's got an on-off switch, so let's see if it works. I know it works. Yep, lights are on. That is St. Albans, believe it or not. And as you can see, it's a very, very weak reflection with a lot of noise that one has to average out somehow. And the averaging was often done on the phosphor, simply by having a long persistence phosphor and a low beam intensity. You could build up an image and make quite accurate measurements. So one of the additions that came along pretty soon was a cursor. And you can move the cursor across that time base so that the geometry of the CRT was inconsequential, and measure that particular spot in time, which of course corresponds to a spot in distance. That thing there, anyone know what that might be? You're too young. Too young and innocent. That, my friends, is where the detonator went. If your plane was going down, the first thing you did is blow up your equipment. That's serious stuff. And I used to buy these things, and they always had a detonator tube. So they were pretty intent on minimizing the evidence that was left behind in the event of a crash. Serious stuff. Now, this is actually the very first indicator unit I used as a kid. These are lovely vacuum tubes called the F50s. This is my little kitten Bisky, who spends most of his life with me. But that's the thing. That's the thing I built my first TV set on. And again, it was only because it was so cheap that I was able to afford it. I had a paper rag, actually two, one in the morning and one at night. And with those few pennies, I could afford that stuff. And I don't think kids today have that. I know they don't. I mean, there are all kinds of blister packs containing funny things called microprocessors, but apart from that, there's no real connection with the visceral world of electronics at large. Actually, I should say electronics at large, because nowadays all electronics is at small and you can't really get to the guts of it. Here's another one. It has two CRTs. What a turn on for a kid. And these are some of the CRTs I harvested. I've still got these at home. I've got, maybe 50 to 70 CRTs and 38 scopes, and I love to collect this stuff. But this one was a 6-inch CRT that had a white phosphor. They usually had a green phosphor. So when you're making TV sets, of course you want a white phosphor, and so the 517 or VSAR 517 was a much coveted CRT. But there are so many more. I made the scopes, of course, with the little beautiful babies up there. And now this is taking another direction. This is still a diode, but this is a diode of a different scale, if you like. It's in fact on the other side of the story. The magnetron is a diode that makes lots of pulse power for transmit. The question is, how do you receive these weak echoes from St. Albans, or from that nasty aeroplane with a swastika on it, flying over the English Channel toward you? Well, you need a receiver. And so the development of diodes was very important. And this actually says D1 on it. It's a development diode made at Malaz. And later it led to this thing, whose number I bet you don't care about, but it was an EA50, or VR, valve receiving 78. And you can see it begins to get a bit more sophisticated. The manufacturing techniques are a little bit more, the pinch here is more regular than up there. But I used dozens of those, and so did radar receivers. And they're little itsy-bitsy things. And a bit later, something rather wonderful called a semiconductor came on the scene. This is a Westinghouse diode, and it's sort of a cat's whisker thing. There's a lump of something like germanium here, and then a plunger that pushes down on the germanium and makes a junction. And these things began to be used in place of diodes because they had no noise, and of course that was in one way the beginning of the semiconductor revolution. I say in one way because it was microwave diodes that led the development of semiconductor devices in Shockley's days rather than active devices. And by the way, the bipolar transistor was not an invention. It was a casual experiment being made on a wedge of germanium, in which two of the technicians at Bell Labs wondered what about putting the whiskers, they were using tungsten whiskers, on the other side of the wedge, rather than making a surface device, which is what they're trying to make. Let's see what happens. It's the what-if syndrome, which I think is so powerful, and I would encourage you to use it every day of your life. But the what-if led to the BJT, and of course Shockley got up in a later meeting at Bell Labs in June of 1947, I think, and made a big fuss about "he told you so," and so on and so on. But anyway, so here's another circular theme. This is a klystron. A klystron consists of two resonators. These cross sections are a little bit hard to understand at times, but these are grids that intercept the beam that's being accelerated towards something called a collector. it's also called a burner because most of the energy of this beam ends up as heat. But in passing through the first grid set, the pair of grids actually, this first, it's called a rhombatron. It's a funny name, but it's a rhombatron, and it receives RF power, which is just coupled in very loosely into this resonator, but it modulates the packing of the electrons. It's a bunching phenomenon. So as the EM field across these two grids fluctuates, it bunches electrons together. Well, that bunch of electrons continues to flow, but as it flows from here to here, it gains this many electron volts of energy. And in so doing, it arrives at the second pair of grids with a higher power than at the input, and it actually is an amplifier. Of course, you get about 5 dBs of gain for about 20 watts of power, so it's not exactly the sort of thing you want to use today, but klystrons nevertheless are still used today. That is an old klystron in my collection, but I'll show you where it fits into the box. So this is actually an oscillator. Here's the resonant rhombatron, if you like. Here's the electron tube, and up here is a thing called a reflector that turns the electron beam back again on itself and reinforces the velocity modulation that was incurred the first time I went through, and the thing can be made regenerative and oscillate. But you can see it's a pretty old piece of equipment. There's a little neon stabilizer, a rather sad-looking choke. Oh, there's a rectifier tube, 5U4, I bet. This is a circuit of a rather bigger klystron, and we won't worry about the circuit so much because I'm not sure I understand it. But this is how it looks big time. What do you reckon that is? 10, 9, 8, 7, 6, 5, 4. It is a linear accelerator. And these accelerators drive the guts, the urging components inside that pull the beam into to have ever higher velocities as it goes that way, or maybe this way, I don't know. But these things run at pretty high power. They're maybe 250 kilowatt output klystrons, and there's a whole bunch of them in here. But this is the same principle as I showed before. However, rather than the two rhombatrons that I showed you in the simplified diagram, they often contain many. Here's a Toshiba, a modern Toshiba klystron. It's funny, if you look at the properties of this, and compare them to what we do with circuits, the inputs are plus 40 dBm. That's a lot of power. The output is 3 megawatts, which is even more power at a pretty good efficiency. There's the burner at the end that gets awful hot, and the input port is here, and you can see several resonators along the length of this thing. But this thing is about 16 or 17 feet long, and it only operates at 324 megahertz, so it's kind of a little bit dismal in terms of what we try to do sometimes in a little tiny bit of silicon. This I just throw in because it's a fun thing to talk about. This is an A to D converter. Down here we have an electron gun, deflection plates which you can't see, driven actually through the pins, however, not through side pins as often the case. And up here is a target that is encoded in a binary gray code. And as the beam is deflected one way by the signal, the AC signal we're trying to convert, it's also deflected this way by a sweep. And so you're making a raster whose values can be read out of this target because of the embedded geometric coding in here through these connectors. I'm not sure why there are two in here, but I've not got one of those tubes. I can't tell you much more about it. But that I did use one, I should say, yes. I used one of those converters when I worked in my first job in a speech encoding system. This is kind of fun. A little bit off the circle theme, but still on the hollow state theme. This is called a selectron, and it's too bad we can't see the bottom here because it says the selectron tube had random access to 256 bits within 20 milliseconds. And that's a treasure. I haven't got one of those yet, but I may be able to get one yet. But they made a big fuss about it. So complex are present scientific studies, such as atomic research, that working out the arithmetic could take all our scientists' time. a shortcut is found in the use of analog electronic brains. Okay, now here's jumping around a little bit. This is, we're going to get to another tube in a moment. Let's see. So many buttons to push, so little time. This was 1947, and this is yet another tube structure. I think the reason why I'm so much enamored of this period of time, apart from the fact that I lived through it, is that it was a time of huge invention in electron tube technology. So many clever things were being done with electron tubes, just by dint of their geometry. What can you do with the geometrical disposition of cathodes, anodes, and so on and so on? And it was that that led me to be quite inspired to do some of the later work I'll tell you about that is very much in the same spirit. So here we have yet a new tube structure, and it's an FM modulator. Actually, the device itself is a phase modulator, as we'll see, but here's a picture of it. This is in a reconstructed transmitter that actually runs. There's the phasotron tube, and there's an electromagnet that accepts the audio input or the music input from the radio station. How the heck does that modulate? Well, these pictures don't help you to understand it too well, but you can just about see a whole bunch of little grid wires here, and there's a cathode in the middle, and those grid wires are activated with the RF carrier in such a way as to make a kind of a waffle of an electron disk that has the modulations. Now, understand that the guy who drew this was trying to suggest the density modulation of these carriers, the electrons, rather than up-down, no significance up-down. What is going on, however, is that these grids are impressed with the RF modulation, and so as the electrons move toward these outer anodes, of which there are two, one has slots and the other is just behind that one, the RF energy passes through the anode slot here when at a high crest, and again that doesn't really mean up and down, it really is more a matter of intensity, but during one phase of the RF, and then during another phase of the RF, the other anode receives the electron flow. So when an English field is applied, it warps this whole waffle in such a way that the phase relationships are changed. I mean, it sounds exotic, and it actually is quite, a peculiar thing. But the consequence was that when we place a tank circuit on the output, so the two anodes will be connected into a tank like this. So the inner anodes get to one side of the tank, and then what's left, that is the electrons that don't go, let's see, well, the electrons that do go through the slots end up at the output anode. And as you modulate the shape of that fan or waffle of electrons, so the phase of the output varies. And the way you make that modulation phase is through that coil that is the modulating coil. Now, since the relationship between applied voltage and the current in this coil is an integral relationship, in fact, it's no longer a phase modulator, it's a frequency modulator over a narrow bandwidth. So, I mean, this is only thrown in as an illustration of the kinds of things that as a kid came into my, field of experience and curiosity. So we're still on this circle theme. Here's a funny tube. Anyone guess what that might be for? I know these are tough questions. I'm sorry to be tough on you. But I do give the answers in the end. Well, would it help if I said that this is a little electron gun down here, and electrons come out like so from this gun? So what do these things do? Don't worry about that. That's just for reference, as if you didn't know. I'll tell you, it's got a funny German name, Baden, Straher, Rover, I don't know, any German-speaking people here. But anyway, what it is a physics experiment, or physics lab experiment, to measure the charge-to-mass ratio of the electron. A gas is used inside the tube to let you see the path of the electron, and you adjust, these are coils, I think there's something like gas coils or some fancy name. And by changing the magnetic field, we change the radius of curvature, which gets us back to the magnetron idea all over again. And those little marks that you could just briefly see in the other picture, these here, those are measurement gaps. They're like meter marks on a ruler. So what you do is you adjust the field until at a very high field, it bends around and passes through those slots, and at a lower field, this and so on, eventually through the slots up there. And as you use a combination of H field and E field, the E field, of course, being the accelerating potential on the anode, you can extract from that the E to M ratio. And it's, as I said, it's just a physics lab trick as much as anything, but it is one of those spherical tubes. Here's another one that was a direct inspiration for something I'll show you explicitly in just a moment or two. It's called a decatron, and a decatron consists of some 30 electrodes, which are all little wires, they're cathodes, vertical wires, and then there's a disc anode at the top of the tube. And you see that the pairs are driven, it's a bit hard to see from this diagram, but they're driven, here's a two-phase clock. So we're actually, first of all, making this very negative, and then this very negative. It's a funny drawing, I'm not sure I can make my way through it, but the idea is that by driving this thing with a clock on the alternating sets of cathodes, you first initiate a discharge here, let's say, by just a random process. It'll pop up wherever it wants to. So let's say it's initiated here. Now you let that go positive and you take this negative, and the plasma is already developed in this region. So the most likely cathode to take over that plasma is this one here, and it does. And now when you release both of these, and they both go positive, there's a gaseous cloud here, a plasma cloud here, and it's these outward electron cathodes that pick up the discharge. And so this thing hangs. The plasma moves around and around, and you can both visualize, I mean, you can both look at the accumulated count, or in many cases, and this might be one of those cases, you simply use it as a counter tube, and you don't bother looking at it, I should say. So I use these a lot, and Decatron, it was a very popular counter tube at one time. And as you saw a moment earlier, that's how it looks when it's running. So let me show you, if my machine will let me. Oh, first of all, here's an ad. So this one allows you to bring out all the cathodes individually. It runs at 4 kc. I suppose you know what kc is. Kilocycles per second. 4 kilocycles per second. With access to all cathodes. That's the GS10C. I've got lots of those. And the GS10D is just meant to be used as a counter, but it'll run at 20 kilohertz. And it also does that with the universally acknowledged decatron reliability. And it was reliable for the simple reason that, like the magnetron, it is simple. It's just bits of wire sticking into not a vacuum, but a neon atmosphere, and it can't really fail to work. So the idea that it can't fail sort of appealed to me, as you might imagine, and in designing some ICs for the 7000 series of scopes at Tektronix, I wanted some counters that had to do a number of different functions, but I thought about making a solid-state decatron, and I did. Oh, here's an unusual example. This is a hydrogen-filled decatron. Do you know why it might be hydrogen rather than neon? Mm. What's the difference between hydrogen and neon? Hydrogen is smaller. It's a faster gas. So these things will zip around at maybe megahertz. Wow. These are called trocatrons. Trocatrons, and I got some of these in my collection too, I'm proud to say. They're heavy because they have a magnet. You can see the magnet in this case. You can't see it in this case. But that arrow tells you which way round the count goes. And in fact, inside this thing, there's the base. It's quite a lot of pins, about 18 pins. But inside here we have, and I don't think I have slides showing this, but there's a series of anodes. Now, this is a vacuum tube device. I think that's the important thing. And again, it's a crossed field idea. The magnetron uses an H field that causes electrons to rotate and to go into this kind of tornado, I call it. And exactly the same thing is happening here. A magnetic field is induced into the structure such that electrons emanating from a central cathode are inclined to move around a set of anodes at the outside, much like a magnetron. But because of the geometry, the way that the anodes are made, in a particular kind of a slotted capturing kind of a fashion, the count can stick at a particular anode and stay there until the next hot box. So these were very important because being vacuum tube devices, they could work very fast. And they were used in computers at the time. The Pegasus, made in Britain, I think, used trochotrons. Hard to find these days. Now, this is my solid-state version of it. It might take a little bit of explaining because I don't show the circuit explicitly, but only how the layout looked. Of course, idealized layout. But these are N emitters. The softer green is the emitter, the bright green is the contact area, okay? The red is P diffusion, which forms a base. So there's the base of the NPN, but there's also an extension of that base, which forms a resistor. And the base goes to ground through a resistor. Then there's another region of this P that forms the lateral PNP. So injection from this P emitter, and all of this, by the way, is in the same epi region. Part of the reason for doing that is that in the good old days, the distance between the edge of the base and the edge of the isolation wall was massive compared to the size of the transistor. Just roughly stated, it's a bit like this, the postage stamp would be the active area of the device and the postcard would be the isolation area, something like that. So you want to try to get rid of isolations as much as you can. So this thing threw everything to the same tub, the same epi region, so everything's connected. So there is connection from here to here underneath by virtue of the resistivity of the epi, but the buried layer, which is in white, makes it more favorable to connect this collector current as it arrives vertically from the emitter to be connected to the base, the active base region underneath the P emitter. So now we have something like an SCR. We have an emitter, we have its base, we have a P emitter and its base, but they're connected in a feedback path, and the voltage that is generated by the lateral transport of current carriers from the P-type emitter is made into a voltage by this resistor. So if I show a little animation, we will end up with this P emitter being active, of course, not showing little bubbles as I show here, but there'll be transport back to the base, in fact, two ways. Furthermore, there'll be transport forward of holes from this emitter into this base, which raises the potential on this base. But so far, this emitter, because the clock phase hasn't yet favored it, this emitter is off. So we have a current delivered in phase one to all the emitters, but one of them gets that current, transports it through the buried layer to PNP, and causes this feedback. We also feed out to another set of cells like this, which provide counter buffers. The counter can continue working and sweeping across the top collectors while the top latches, and that's something you just arrange by relative magnitude of bias currents. So this is very tiny, and certainly by the rules of the day, it was far more dense than MOS was. There wasn't much MOS, as a matter of fact, at this time. So we get this same transfer in one direction, just like we did in the Decatron tube. So that was directly inspired by the Decatron, and they're used in in lots of applications today. I still use them because they're so powerful. You can get a divide by 10 into far less space than using binary JKs with feedback in a bipolar embodiment. I'm not sure how we'll do this in an MOS embodiment, CMOS embodiment, but I've made these in very dense silicon germanium processes just for the fun of it. And that's, by the way, that's why you should do a lot of things. It's just for the fun of it, if you get the chance. Now, this was a moment half of my lecture is falling down into the floor. We've got to fix this up. But anyway, I'm just kidding. This was a major epiphany in my life. It was in 1958, I think, that I saw my first Tektronix scope. And it amazed me because it worked. It did everything it was supposed to do. So up here we have a thing called level and trigger slope. And sure enough, if you change the trigger level, you can see the trigger point going up and down a sloping edge of a pulse here or something. And trigger level, if you flipped it, sure enough, it went to the other edge. Everything worked. The time base was calibrated. It had all these plugins. You could plug into different things. It had calibration outputs. It was lovely. I got several of these in my home collection now, and I sometimes use them. But it was a moment of inspiration. Now this date is, it doesn't show on it, it says 1960. That was the date I did my own sampling scope, which we can't read because it's off the page here. But I was so enraptured by this, I decided I was going to build a scope just like it. And so ordered a lot of parts from Tektronix, the CRT and the knobs and other special parts, and put together this. So here's brand VG, and here's brand Tektronix. It says Demonstration Sampling Pro. Pro was capital Gray oscilloscope. But what was neat about this was not only did it have a set of plugins doing different things, and these are precision offsets that allow you to make voltage measurements, this was all sampling, and this was real time. And so when you put this thing into delaying sweep, you can't really read it here, but you switch to delaying sweep, it became a real-time scope and used a real-time ordinary time base. When you switched to delay ed, it changed gears and became a sampling scope. And so the little brighter region that showed where the sampling time base would run became transformed into a full screen signal. And I could say a lot about this thing, but it was a labor of love. The neat thing about it was that way back then, in 1958, when I started on it, it used only the available, it used nothing but transistors for the time bases and amplifiers. It used one or two vacuum tubes for deflection plate driving, cathode followers, but it was using the transistors of the day to achieve about a 700 megahertz bandwidth. And that was a remarkable thing about sampling. It really turned me on, because with all what followed was sort of audio frequency circuitry. Once you've captured the sample of the signal, you stretch it in time and you can process it however slowly you like. And another thing this thing did was it drove a pen recorder, so you could get beautiful high quality paper recordings with the noise suppressed by a mechanism which, if you're interested, come and ask me about it later, but it's a very powerful noise reduction mechanism. And so I was proud about that, and I got to Tektronix on the basis of that work, I suppose. This is just, oh yes, another novelty here was the use of feedback. Normally at that time, samplers were very crude. There was basically just a diode switch and then an amplifier was all open loop. In this case, we take a little brief sample of the signal, and this capacitor doesn't charge up fully to whatever the voltage at that instant is, because there's a resistance associated with both the sampling gate and of course the source. But it charges up to the same amount every time, same proportion every time, and that's amplified in this thing, which can be called a pulse stretcher. There's a second integrator that puts it into a final capacitor that holds the charge. And now here we have a replication of that signal, but with some uncertainty, because of the uncertainty of the efficiency here and the uncertainty of the gain and so on. However, by feeding that signal back to the bottom end of this leak resistor here, during the time between samples, this recharges to that voltage. So the next time the probe at the sampling gate closes, it only has to convey the error between the present sample and the last sample. So you end up with a response to something like this. This is when you've deliberately rolled off AL to the point where it's about 50%, and it creeps up this way. If it's too high, it'll hunt like this. And this was often used to lower the noise at the output by effectively putting in a low-pass filter in a kind of switch capacitor mode. But I sometimes look at this and I think, well, it was pretty neat stuff at the time, and the fact it all worked was even more amazing. So there it is. Of course, this brings back nostalgia to me that it won't do anything to you. This is a pulse generator. Oh, well, yeah, long story. I won't tell you the whole story. But there's the other plug-in, and eventually we made a whole bunch of these things as sampling adapters that worked with that scope from a company called Solutron. 100 of them. And guess who was the guy who had to make them all work? This is about paper circuits. That's one of my cats. I think we've met him before. He's Biscuit, the Tonkinese. That's a bit of my study, a bit of a mess. But when I say paper circuits, you'll probably wonder what I'm talking about. And there's actually two interpretations. Here's one interpretation about character generators. But I mean it in different ways, we'll see in a second. But this gives you some idea of the kind of trouble that people went to. This was Lincoln Lab's work. And the next page perhaps is even a bit more descriptive. You may be able to see there's a whole bunch of transistors here, but these are transformers. And they have 60 kilohertz, 30 kilohertz, various frequencies where they're supposed to work. And they're taking a whole bunch of little bits of sine waves like this and turning them into characters. It was kind of wondrous, I suppose, but so complicated. So I was determined to make a readout system for scopes for the first time, and it was going to be simple. This is how it ended up. This is a side view of a 7000 scope. There's the readout system. The rest is time bases and so on. That's a plug-in, of course. So we just take off the side of the scope to get that view. And in there are 14 ICs I did in 1 year. I think probably one of my most productive years. And this is how I started. Here's where the paper comes back. This is Teledelta's paper. It's a paper that is coated with carbon, and it's resisted with a sheet resistance of about 2K per square. These are silver paint lines that I painted actually with a paintbrush, onto the edges of the stop sign shaped region of Teledelta's paper. And these are little contacts that in this case are meant to generate the character 3. The output currents from the upper and lower contacts are taken to the Y amplifier, and from the left and right contacts to the X amplifier. And of course you can see intuitively that this is not going to be linear when we start dividing current up in that field, but we can put the dots where we want and make it linear. So let's apply a current to this dot. Then the currents divide up in the way shown, and a position appears on the CRT corresponding to the division of that current into its 4 components, or principally the X and Y components. Now, if we apply half the current here and the other half of the current to this dot, then it's as if there's a phantom point in the middle. I think you can see that intuitively, but you know, it maybe take some believing. But so we can move the dot on the CRT from left to right, and we continue to do that by applying a series of currents around the, in this case, the particular character 3, ending up with all the current flowing at the end. And of course you need many of these. So in the demo that I made to show the president of the company, Howard Bond, I made 50 of these, so there were all of the numbers and all the alphabetic characters and some other special signs like mu and things like that. And these were on printed circuit cards, and I had it all working so it made sense on an oscilloscope. And he was sufficiently impressed by it that all the other methods that were being discussed at the time for readout in a scope were dropped, one of which was the use of an optical encoding disc inside the plug-in with coherent optical fibers through the interface up to, so unfortunately the guy who had that idea, Hiro Moriyasu, died of electrocution in his own workshop a few months ago. He was from Japan. He saw the first bomb dropped on Hiroshima, and his folks were killed during that time in the bomb raid, and he lived, and he was raised by monks, and eventually came to work with Tektronix, and he was highly regarded. Very quiet guy, nice guy, but that's what happens to nice guys. Now, you may be asking, it doesn't matter. I made contact to all these little silver blobs through little fragile wires, and they're driven by a circuit down here that takes a bit of explaining. I think, I won't bother right now. I call it a Kermit. It stands for Common Emitter Multi-Tanch, and it makes a series of Gaussian shaped current pulses with respect to the voltage difference applied to the two base ends here. So we can scan these points by the use of a waveform that doesn't have the abrupt discontinuities as, say, a triangular wave would. that results in a certain amount of smoothing of the character, but it was permissible. But I've used Kermits over and over and over again, and you could write a book about them. But not just that one circuit. So this was the next development. I mean, the first was the demo for Howard to get hooked. The next was to make these things. I had the silly idea of keeping the shape of the character in the monolithic chip. I wanted to see the character down there under a microscope, which was dumb. But anyway, that's what I did. And so now we have base contacts to, of course, contact this region, collector contacts here, and this is the epi region, and these are N emitters. So again, there were 50 of those, one in a package, and they were connected up again to this Kermit in this particular way, so that they all had a chance of receiving, let's say, this first current. So the current flows in here, and then with a Gaussian transition flows in this collector, and then whoops, this collector, and so on. So when the current is mostly, this is the emitter current that you don't see on the bottom of the page here, but this emitter current is mostly flowing here. It's applied to all of the first dot, the first position on all of the character generators. But because the bases can be selected, you pull up on one of the bases through, I'm not sure I show the wire here, but on one of these bases we make the potential higher, and that favors the current flowing into this character or that character generator. And so that's how the selection was done. And, you know, it worked, but it wasn't very elegant. This is just how you can view it, but I wanted to get to the next step. So this is how that original looked. It had an array of, I don't know, over 100 emitters, and you just picked up the emitters you wanted with metallization. And, you know, this is sort of how it looked in a little demo of a curve tracer. But, you know, it's sort of, it's pretty obvious, I think, that this isn't the way to go. It's too clumsy, it's too area intensive. But there we have, for example, a wiring up for a letter 2, for a number 2. Now the next step was to use the emitter position up and down a long base region to generate the y and the x coordinates. So the currents were divided, and this is 10 characters now, the currents were divided into x and y components just depending upon their physical position. So I think I have a little sort of animation here. You see each of these emitter pairs are generating a particular point XY point on the display. And this was driven by our old friend the Kermit, a pretty clumsy big thing in those days. Kermit 8. So the next step, which was the final way of doing it, was much cleverer. It was, when I say clever, I mean much more decent, you know, much more elegant. So it uses a set of transistors having 6 emitters each, and then by selectively connecting a number of these emitters to make the x coordinate, and a different number perhaps here to make the y, and throwing the rest away as a z current dump, that current coming from the Kermit that's scanning these characters gets divided up into x and y in accordance with the very simple proportional representation shown on the right. And this was a sort of scale of things, so here would be a main character, but then you also have some below the line whiting area, but you're constrained, of course, to the sum of the two currents, the two coordinates, I mean, being less than or equal to 1. So it was a bit funny in some ways, but it turned out you could generate all the nice characters you wanted to with that. It was kind of fun to generate a font set to be most visible. So I go on at some length here about defining a symbol for one of those stages and so on. And then that was a bit from the paper that was about it. And this is the chip that eventually called the M25, I think, as I remember. And so here are the division areas, and our old friend the Kermit down the middle. There I show some of the points that were available to put the characters onto with 6 emitters in each transistor. It was high time, a lot of fun. That's the main thing. Now, still at Tektronix, where I had a lot of liberty to kind of do things that I thought might be fun to do. I developed some super integrated devices. Now, you've already seen a super integrated counter. That was the thing that was taken from the Decatron book. And by the way, I call it a string counter because it is a ring counter, but it's also like a skinny string. So here's the circle again. I really wish I had some other pictures here because this doesn't really explain the whole thing. This is from paper, JSC paper. It's about a semicircular region of conductive material. So it's a D-shaped region of conductive material, and I did the experiments with teledeltas paper. My son took down the DBM readings as we worked at home on this. We've also used pudding bowls with salt solutions in them and so on, but we had a lot of fun with this stuff. Here's the thing, takes a bit of explaining, but if you apply biases to the top ends of a D-shaped region, current biases, there'll be a certain point around the circumference where the potential can be made to be highest. And by changing the ratio of those currents, you can move that high point of potential around the circumference of this region. Now you can imagine if that region is a base of an NPN transistor, and we put an emitter in there, which is a half of a ring, and then put a collector underneath, we can cause the injection to occur over a very limited span, a limited angular range of that emitter, where the base region is most positive as induced by these external biases. Now this was just simply to show that I determined experimentally that the relationship between the injection angle and the bias coefficient, I used maybe X here, that experimentally my son and I working together, of course he wasn't doing much of the thinking, but that's okay, it was fun. He and I found that the relationship was an inverse cosine relationship. And I wanted to prove that, so I did a conformal transformation. I simply, first of all, completed the circle, since it's perfectly symmetric from that point of view, it doesn't matter. Whether it's a complete circle or half a circle, and then transformed that into the infinite plane with this transformation, and did the analysis. And sure enough, you find, lo and behold, it's an arc cosine. It doesn't get the end of the analysis here, but it is an arc cosine relationship even in theory. Now, I may go back to that. The reason why arc cosine was interesting was that as the domain moved around the emitter, the amount that went left and right was a cosine relationship, of course, being a circular path. So the arc cosine, in response to the modulation voltage, was cancelled by the cosine relationship in the collector, and the overall transfer function became linear with regard to what I call the X input. The Y input is a completion of two complete halves, so the Y input was the magnitude of the current supplied to the two emitters. And that was very linear because that's just it's just a cascade from an emitter down into the base and then into the collector region. The thing I didn't like much about this device was that there was a lot of redundant capacitance, because really the only active region of interest is where the domain is, and all the rest is just parasitic. It was still pretty fast. It was about a nanosecond rise time when the domain was pretty much well over toward the contacts, and I think it became about 3 nanoseconds over here somewhere. But it was a good proof of concept, and I wrote the first paper on that, and then a guy called James Smith, very strange name, he wrote a follow-up paper, and I can give the citation if you want. I was going to show you some other stuff here, but let me jump to this one. This is a solid-state potentiometer, and the idea here is to follow up on that same idea. Now we're out of the circle theme a little bit, but this is an N emitter. This is a P gate, a P channel gate, a PMOS transistor, and so is this. And so the MOS part is symmetrical, and they both point inward toward this region, which does 3 things. It is the active base region for the NPN, at least the emitter is the active region, but it's the base for the NPN. It is a resistor from left to right, and it is the drain of the long PMOS transistor. And I think you can see that if we bias up the PMOS transistor gate to source equally along the length of this device, that the current density is uniform all the way along. So we have a sheet of current, of uniform current density from left to right, and it's balanced on the other side so there are no big transverse fields under the N emitter. Now, I think it's fairly apparent that if you have a sheet of current, of constant current density, injected into a long resistor like that, you end up with a parabolic distribution of voltage. So if you tip the ends of that device linearly, then you have a new parabola whose maximum occurs as a linear function of the applied voltage. You're just moving left and right, and it's a perfectly linear function. So now we have a much more concentrated domain and a much tighter device, but furthermore there's a buried layer under here, which I think I show elsewhere, but there's a buried layer which forms the resistive tract, if you like. Think of this as a potentiometer in which we're making a domain, which is like the slider, and a resistive tract, which is the output. So there's not much consequence of the epi region here, because the epi is very high resistance, and it's in this buried layer where most of the current division occurs. So I think maybe, yeah, well this is our old friend the Kermit. What I'm saying really here is that it is a solid state Kermit. It's just a continuous form of the Kermit. All of the emitters are tied together because there's just one emitter, and these are those fragments of the base, and these are the currents coming from PMOS devices. So we generate this domain. It actually is a Gaussian shape. If you think about it, you have a base emitter voltage difference between one device and another, which has a form exponential minus x squared. You know, x squared because of the shape, so exponential minus x squared, by the way, that tells us it's going to be a Gaussian kind of thing. And sure enough, it is Gaussian. What's nice about it, amongst other things, so here's our domain. As temperature varies, the width of that domain varies because it's all scaled by kT upon Q. We could avoid that by using p-tap biasing into the base, but then the scaling would p-tap the base port of the system. So, but it doesn't matter because this domain acts as if it's a point, a concentrated impulse function of current at the center of the domain, and as temperature varies, it may expand or narrow the domain, but the centroid stays the same. So this pointer on the resistive tract stays, right where it should over temperature, except at the very ends where anything's but so it's a workable device. You can easily try it if you've got access to a CMOS process. So we started with this picture, and I wanted to get back to something that's very closely like it. This was 1940, and this was 1970. This is a carrier domain magnetometer, and again, like all these super integrated devices, it takes a bit of explaining, but there's an N emitter at the perimeter of a big base region. So there's the edge of the base. There's a gap where we see down to the epi, so I should have used different colors here. But that's epi, and then there's another ring, which is an outer P ring. And then in the middle, we have a contact to the epi and a contact to the base. So it's sort of a transistor. Actually, it's more like an NPN-PNP combination. I think maybe I can show that somewhere here. Yeah. So looking out from the center connection of the epi, the center of the base, and so on, we have the enemy, the lateral PNP. Actually, this doesn't quite show things as they are because there's another junction on that side. That doesn't matter. And the drawing doesn't quite show, but I think you can guess that this is a NPN-PNP combination that acts like a little SCR. So when the currents are turned on, there's a perfect current source, in principle, applied to the lateral P emitter and to the N emitter. And that current has to go somewhere, and it goes at some random point around the perimeter, which is a region where the carrier injection is very crowded because of the feedback of the PNP and the NPN. It's a very intense region of injection. So going back to the surface view, those minority carriers that are moving laterally from the P emitter back to the edge of the P base are influenced by a magnetic field into the plane of the paper. And they rotate. The domain rotates. So it's hard to animate that perfectly, but you can see that something like this is going to happen, and sure enough, the domain does rotate, and the rotational frequency is proportional to the H field. The problem that we faced with the actually, I took these devices back to Britain when I went back on a long sabbatical there, and they were examined at the University of Southampton and the University of York, and they had to use a nuclear magnetic resonance magnet in order to get the domain to move. The problem is stiction, because the reason that domain came alight in a certain place is because that's where the misalignment of the various layers favors the appearance of that domain. But you see, I was taking another leaf out of the magnetron page or the decatron page, the same basic idea of having something that can be forced to move rotationally around a circular perimeter. And however, it was not all lost, because I suggested next that we take a leaf out of magnetic recording book where you apply an AC field to a tape in order to overcome the hysteresis of that tape and render the overall modulation onto the tape linear. So a device, this wasn't quite how the device was, I was trying to simplify it, but the external emitter ring, these collectors, they were divided up into segments, and they came out as separate collectors, very much like the cathodes on a decatron. And they could be connected to an up-down counter. So if you apply an AC field to this device that is large enough to overcome the stiction, then the domain will rotate in one direction and then rotate in the opposite direction alternately, and the accumulated count in the CMOS counter will be 0 after one complete cycle of the AC excitation. But if there's, in addition to that, a DC field on top of the AC field, or of course if the AC field should be unfortunately asymmetric, then there will be a count accumulated in that counter. So the appeal here, the big deal here, is that this, to my knowledge, is the only kind of magnetometer that is an integrator. You think about it, most magnetic sensors, in fact I think all, have a spring return kind of a mechanism. For example, in a Hall plate, carriers are deflected to one side by an H field, where they generate an E field, and the E field prevents further movement of that current path anymore toward the edge of the little square slab that makes a Hall effect sensor. And other sensors that, rather than being circular, they're based on this idea of the SLIM, which is a steerable localized projection. Look, sterilized, localized. Let me try again. Reset. Steerable, localized injection multiplier, SLIM, which also describes how it looks. But taking a leaf out of that page, you can make SLIMs in which the domain has no preference to be anywhere along any part of the emitter. So the light up somewhere, once again, stiction may be concerned, but because of the parallel nature of all the diffusions now, it's less problematical in the circular configuration. And what you end up with is something that can be described as like a steel ball bearing running in a little half-cylinder track cut into a steel plate. So the ball bearing's in the middle. As you tip it, it jams to one end. As you tip it the other way, it jams to the other. So it's a magnetic comparator. And then with a coil, now not used for the purposes used here, but a coil that the current in which just brings that domain back to the center, then you know by direct measurement of that current that it is directly proportional to the magnetic field. That's not quite an integrating, it's almost an integrator, because as a magnetic comparator it has very high gain, analogous to the high gain of an op-amp, which is supposed to do a lot of things even though nothing much happens at the input. So these mag sensors have worked out pretty well. But again, the point that I'm trying to make, if it isn't very obvious by now, is that all of these ideas are really just the same idea, spread on the bread in a different way. It's only a few ideas, and it's amazing how far you can get with just a handful of ideas like that. So let me see if I got anything. Yeah, I think I've got just a minute or two to talk about this. I of course would love to talk more about translator design. The reason I'm talking about computation at a loop or a node is you can do remarkable things just by this simple invocation of tying a lot of emitters together and arranging for a loop of junctions. But it's amazing partly because of the amazing properties of the bipolar transistor, but a cautionary note can be, what should we say, injected here. is appropriate. That's what I'm trying to say. A cautionary note is appropriate. And that is that today's devices are very tiny and they have very high thermal resistance. And so translinear circuits don't work too well. Because even a very small amount of heat can raise the temperature sufficiently to throw a spanner in the works. I mean, I'm not saying it can't be done, but you've got to use big emitters, and, multiple stripes and so on. And you can actually, I use translinear circuits a lot. I shouldn't say it can't be done, but it's a bit harder than it used to be. And if you read in textbooks about little VGA cells that are supposed to be nice and variable gain amplifiers, forget it. I'll tell you why later, but they don't work very well. So I like to call the bipolar transistor the mathematical transistor because of this simplicity of its behavior. So this is just jumping back again to the early Tektronix days. The question arose between myself and George Wilson, can we do any better than this classical mirror because we've got the aerojuice beta and so on? What can we do? And as an aside though, looking back, it is the first example of a translinear loop because this is the loop in question. There's only two junctions and it is a unique element that can only be done in transistor way. It couldn't be done in vacuum tubes, and it can't be done with depletion mode transistors. It can be done with enhancement mode devices. So it wouldn't work with triode vacuum tubes. So it was a new entity, and it had this rather interesting property that it could replicate a current applied to its input at its output. And this led to a lot of people getting all excited about current mode, this, that, and the other. One of those people was me. Since got over that. So if one mirror is good, two are better. So let's take two of these guys, and notice that we might have connected the two inner nodes, but for the moment, treat them as two mirrors, and there's no cross-breeding between them. What goes on in here has got nothing to do with what goes on in the room next door. But if we break that connection from ground and apply a current in a tail, we suddenly have a truly new cell. And I want to emphasize this. You should be asking that every moment of your life. What if, what if, what if, how about, maybe, will this work? And it doesn't matter if it doesn't. No one knows. It's just between you and your computer if you're simulating stuff. But ask what if all the time, because it's such a powerful question. And of course, when things don't work right, you ask why. And you don't stop until you find out why, and then you go on with another what if. So I'm trying, I guess, to provide a philosophy of life here, but that's my view, and I'm sticking to it. So you end up with really a new current mode cell. And it does some interesting things, and I'm not going to go into a great length except to say this was the start of the translinear idea and the current mode idea. And there again is our circular loop theme and the dot theme. So as I say, these are very powerful questions, and you can hope that you're going to get to the next step through some kind of clever analysis, maybe. Maybe you're going to hope to get the insight through mathematical approaches. I'm not, for the moment, casting aspersions on mathematical methods, but I see the mathematics as coming afterwards. Think about the what-if thing. Think about some possible answers. Then the math is there. It's a tool. You use it when you need it. But just as you don't build a house by looking at a hammer, but you need the hammer later on, I don't think you jump immediately to mathematics to get the insight you're looking for. Some of the insight, though, as I've mentioned to some of the students already, can come through using a simulator, because the simulator contains or embeds expert knowledge of tens of thousands of hours. And if it isn't reliable by now, if simulators are not reliable by now, so many years after the 1970s at Berkeley when SPICE was first developed, then something is seriously wrong. And of course, every company has its own, I don't know about every company, but at least Analog Devices has its own particular flavor of simulator. We built our own from the ground up. We have a new one right now that's just come along that we're getting used to that does some pretty remarkable things. But you can ask what if of the simulator. And again, unless you've got someone like a boss, I hope you don't have a boss. That's the worst thing I could wish for you. But if you have a boss who's glaring over your shoulder, you might be reluctant to try some of these what-if experiments because it can look very dumb when they don't work out, which is 90% of the time. But if you have the freedom to work at home with a little laptop on your knee and a little kitten beside you to keep you company, you will have a great deal of fun just exploring ideas and discarding them almost as quickly as current carriers fall out of a piece of wire. So another approach, of course, is the how about, which is really the same thing. And there are more of these little sort of axioms that I would recommend, but I certainly would recommend you indulging in invention as a way of life. I guess, I'm not sure where this fits quite, but this is another translinear circuit, and the loop and dot theme will show what I was showing off, but this is rather cute. It's an analog array normalizer. So its inputs are a series of values coming from some sensor. Bear in mind that in many cases, the information in a wavefront comes about from many different directions. So, for example, in sonar or in seismic activities, you're not looking for absolutes. The absolutes don't mean much. It's the relative magnitudes of an array of signals coming from an array of sensors around the area, and those are taken as a vector that contains the information you're looking for. So this was an analog approach that did that very quickly. These currents just need to be proportional to the inputs applied to coming from the sensor, but the dynamic range at each of these inputs was, in an actual product that used this, the 8638, were over a dynamic range of 60 dBs. So 1,000 to 1 variation on the absolute magnitudes of those currents would be encountered. But on the output side, all of the emitters are tied to a fixed current source, IY, and the ratios applied to the input set of devices is replicated as the identical ratios, correspondingly, in the output pair of output devices. So suddenly we could go from a very big dynamic range of the input to a set of outputs that bore the same proportional relationships. We don't really care what the emitter voltage here is. The voltage doesn't enter into our thinking process. It's all a translinear approach, and we're talking about current mode loops, and I think I have a little yeah, that's the overall function too bad I'm losing all these pictures. That's the overall function, but it says that the output at any of the collectors IW is equal to the input to any of the input nodes divided by the sum of all of the inputs times IY. But in fact, there was another trick in the 8538, which was described actually in a Journal of Solid State's paper of the same title, was made to in a feedback loop. So I made it so that the maximum output from all of these 16, there were 16 inputs and outputs, the maximum output was held at a set point, which was a full-scale capacity of an A to D converter. And then all of the others took up the relative positions in a ratiometric fashion. So that little loop just changed the IY to make that happen. Okay, now this is what I thought I was going to put later, but you've already seen the guy's picture. That was the guy that said there was so much cheap electronics available when I was a kid and so on. And, man, I could have written that. It happened just like that to me. But one of the things that Carver Mead said is you listen to the technology and you know these things are real and intuitive. They're not, mathematical entities. They're not. We don't really care if electrons are wave functions or particles. I mean, certainly in a discussion around the dinner table, we might well talk about that. It's fun to think about it. But as practicing electronicas, we can still get by for years to come thinking about electrons as little balls that fly around inside transistors, and as currents, as electrons falling out the ends of bits of wire and so on. There's no harm in that. It's just that he would say they're totally real, like water coming out of the pipe. He was close to a hydroelectric plant when he was a kid, and he feel that these things were real. I think, if I can say something I think I touched on a moment ago, I think it's a shame that, and I may not be right about this, but that modern youngsters, of your kind of age, really are deprived of having a lot of hands-on experience with very kind of rudimentary things. I mean, when I was young, not that you should do what I did, but resistors were like fuses. They were big things with sort of semi-pointed ends, and they clipped into a holder. And you could pull out a resistor and clip in another one. I mean, this wasn't experimental work. This was how the resistors were made. And then vacuum tube, they had just a 4-pin thing. You screwed it down with some wood screws and wired it up with twist nuts and so on. And it was all very hands-on, and you felt for what was happening. And nowadays, when I look at a schematic, I feel like an electron. I mean, I think like an electron, think like a transistor. I ask myself, this is a high-speed process. Is that transistor going to think it's supposed to be an oscillator? You know, we touched on this morning. Because, you know, it'll do what it's supposed to do. It'll do what physics says it must do. So don't get misled by too superficial a simulation study of some system where you put a lot of effort into the big important signal path stuff, and then you have some bias cells and some maybe audio interface or something you stick on at the end, and those are the things that let you down, because the audio output, the headphone amplifier thinks it's a 10 gigahertz oscillator, and the band gap screams like a banshee at 15 megahertz and messes everything else up. So worry about those things. Worry a lot. When a circuit is giving you a little evidence that it's not doing what you want it to do, that's a little cry from the heart. But the important thing is, if you can, find a lab. I'm sure there are labs here. I'm sorry to be so ignorant. I only just came on the scene this morning. But find access to a lab and a scope or two or signal generator, whatever, and mess around a bit. Because, you know, the simulation studies are great fun and very informative. But now and again, it's fun just to make some resistors blow up and, you know, damage a few transistors and have to throw them in the waste paper basket. I don't know if you've got transistors like that. I've got stacks of old transistors at home. I'm always going to say if you want me. By the way, a sort of a semi-offer I made, and to be honest, I'm a bit, going a bit beyond my permittivity here. We run a lot of project wafers from my lab. You know, from pizza wafers, whatever, because it's very important to have an opportunity to try out crazy things like these super integrated devices and just see what they do. And they only get a few days lifetime when you get the silicon back before they're thrown away. If there should be a good cause, you know, and I mean, maybe I set myself up as the judge of that, I don't know, but if there should be a good reason for wishing to try something like that, let me know. You know, Professor Midge can give you the email address. It's just my name.animal.com. But, you know, it's possible we can just put those stowaways onto a project wafer and try a few things out. Particularly with regard to devices. You know, circuits, they can't be too big before we'll say, well, you know, can't you simulate this? But if it's very high frequency stuff, you may want to make it just because, you know, the simulation's a bit imperfect. I know that you have access to MOSIS, and that's okay, but, you know, it's not exactly an advanced CMOS process. We have some pretty advanced, you know, silicon bipolar processes and by CMOS now. So just bear it in mind. We also actually run on TSMC's shuttle occasionally, but I'm not the best guy to talk to about that. But it's something to explore, because I know, you know, how difficult it is to get access to, you know, some of these weird technologies. And I suppose to some extent I have a slightly hidden motive in as much as I'd like to encourage you to think about bipolar transistors. But anyway, that was Carver, dear old Carver, Mr. Einstein II. He's now deeply into understanding the quantum world, and I think he's on the right track. I was saying in an earlier conversation, one thing we can agree about is that the real world doesn't depend upon us observing it. That seems to be such a ludicrous idea. I just can't believe anybody buys that. You know, the idea that the cosmos suddenly disappears because we're not glancing in the right direction when the moon is up, give me a break. So he's a good guy. You know, neural networks are one of his older things, but he's sort of gone out of being hot on neural networks these days. And one of the reasons is that you understand neural networks are so hard on the interconnect frontier. That's where our brains differ so much, is the hugely interconnected nature of brain cells. I'll just say briefly, since I'm not entirely out of time, that, and you may know this, so, you know, forgive me for saying the obvious, but in the cortex, if you take a cortex out of your head, it's not a good idea to do it too often, but if you take it out of your head and lay it out flat, it's around about 2 feet square, as I understand it. Sounds like a lot, but anyway. But it's 4 millimeters thick, and here's the interesting thing. In those 4 millimeters, there are 6 layers of computation, if I can use that word. And there are connections both transversely between cells and vertically down into the other sections of the brain and crossing over to the other side of the brain in places. What is rather interesting about that is that all mammals have the same 4 millimeters of thickness as we do. They don't have as much spread out, they don't have as many cells, but that structure is uniform. And it's some kind of a computational structure that the creator thought up, and it seems to work pretty well. But again, I agree with Carver on another frontier. He basically says it'll be a long, long time before we can ever make anything resembling a brain in terms of its capacity for information processing, for artificial intelligence, whatever it is we're getting it to do. And I'm sure all of you, no matter how old or young, have pondered on the peculiar nature of consciousness. Well, our circuits have a load. The signal goes somewhere and it causes the motor to run or resist to get hot. What's consciousness? It's a dead end, and yet we know about it. So, I don't know. I shall never understand these things as long as I live, but it's good to be a searcher, I think, and to give some thought to strange things. So I'm about done. I hope it was worth coming to. I've got more cogent lectures I could give. This was meant to be a kind of a philosophical ramble, which I guess has already turned into being. But I mentioned to Professor Minch that if there's an invitation to come again sometime, we can do some serious discussion of some serious circuit ideas, rather than just scraping the surface of noise as we did this morning and talking nostalgically about the good old days as we're doing right now. So thank you for your hour and a half of attention. If you've got questions, I'm here. You are dismissed. Yes, sir.
So you mentioned that when you were young, you got to actually play around with a lot of physical things. Do you have any ideas for how we could try to bring that experience back? Because, I mean, hobby electronics is sort of picking up again, except it's now in a very digital space. So a lot of hobby sites are popping up with people working with little microcontrollers. They're really making that technology more and more accessible. Do you have any ideas on how we can make sort of the old school analog electronics more accessible?
Well, no great ideas, but of course it would be nice to find contacts with people who have components that they're only too happy to get rid of. I mean, there's still a lot of components like that out there. There's a store, now this doesn't answer your question, but there's a store close to my lab called Surplus Gizmos. And it's a great deal of fun to go there, just buy these dumb things, relays and motors and stuff, but he's got them. So they must exist here as well, I would think. And so finding some place like that is one possibility. Another is just being a little bit, what should we say, a bit of irritant is the word I'm trying to avoid saying, but being a bit of an irritant through email to folks like myself and others you may hear about an analog device and say, can you provide these parts? No, I think you have a parts access, to modern. One of the problems with modern ICs, as we well understand, is they're so darn tiny, very hard to work with. I mean, we work through microscopes, and if you can find some way here of mounting those things onto a board which gives you access through bigger pins, then you can do your big, hands and fists manipulating of those circuits. But I don't think there's a quick answer to that. It's just where do you get old components? There's no military surplus to speak of anymore, that I'm aware of. There's eBay, and I've spent a lot of money on eBay. No kidding. I'm into Meccano, which is an old construction set that used to be made in Liverpool in England, and I spent $18,000 just on Meccano parts. So you can easily go out of control if you're not careful. But it's a good place to, there's old vacuum tube sites where if you really want to play around with old vacuum tubes, just because you want to see what happens if you light up a filament, apply 100 volts on an anode, and wiggle the grid voltage, just see what happens. I don't think it's not going to get you any hugely valuable insights in the sense of helping transistor design, but on the other hand, it may remind you, or it may reinforce the realization of how wimpy some of those devices were, how little GM they had to offer, how noisy they were, how microphonic they are, And you get to learn that and you go, yeah, I remember vacuum tubes, and you have this little fond feeling about them that you don't have just looking at a picture of them. And certainly a lot of these, these rare but nevertheless still plentiful available components are fun to play with. The Decatron, I mean, I don't want to make that the center of attention, but you can easily fire up a Decatron with just a 120 volt supply and a little clock pulse generator, and you can watch the plasma go round and round, and folks can say, isn't that cute? But at the same time, you're also getting a feel for, gee, look how slow it is. I can only make it go at 100 kilohertz. I wonder why that is. Then you, of course, you start, maybe you'll even consider the nature of a plasma discharge and how long it takes to make plasma and how long it takes to decay, going back into more of a thinking mode than an observational mode. But does anybody else have any ideas about how to make this easy? Particularly some of the leaders, the movers and shakers of this establishment? I know that Professor Bowman at RIT is a big fan of hands-on experience. He calls it his practicum, and he has lots of... Actually, it's rather fun. There's a microelectronics lab there that has a study called... I wanted him to call it the Gilbert cell. He called it the Gilbert study, but it was etched in glass before I had a chance to suggest. I knew it was going to happen, but I should have said, make it the Gilbert cell. I mean, that's a bit more fun, Whatever the Gilbert cell is, by the way, I don't know what that means, but... no, I really don't. People use the name for all kinds of different things. But there is a little study there where I wanted it to be like a study in Einstein's time, with sort of thick carpets, old carpets, a phonograph with a horn, no calculators allowed. You go in there, you talk about things without the help of your laptop and so on. But it didn't work out that way. It's a modern study, and sort of a little thinking spot like you have here. But anyway, he greatly believes that his students should have a lot of time at the bench, just playing with circuits and just seeing what happens. Let me say one thing that sounds like it. Gosh, what on earth has this got to do with anything? But when I was saying playing with things, one of the things that we play with as analog is or are op-amps. And I just want to say something that I've got to get off my chest here. An op-amp is not an amplifier with problematical high-frequency behavior. It is an integrator. Think of it as an integrator, and you can't go far wrong. That is to say, the gain is almost over the entire range of frequencies that most of us are interested in. The gain is just simply declining at 60 dBs per octave, 20 dBs per decade. And an ideal integrator would indeed have infinite DC gain. So that would meet the criteria required of an op-amp. But thinking about it as an integrator, you cease worrying or cease treating its behavior as if it was a nuisance and something that you've got to deal with later. It's something you deal with right away. So whenever you're using an op-amp, say this is an integrator and its time constant is, and of course it's defined by the unity gain frequency. It's that simple. So that's just just a casual thought. But I can see a lot of students playing with op-amps and making filters with them, and they don't behave quite right, and then the realization comes, oh, it's that problematical excess phase. Well, it's not excess. The op-amp is doing what it's supposed to do, which is integrate.
That's how we actually covered them in our first semester course. Yes.
Oh, goody. Okay. Good. Well, you're in good hands then. It means I can go home. Okay. Well, I've enjoyed being here. It's always hard to know what to talk about. You try to sort of pass on some of your experience and insights and things you believe are important, but in the end, all of our lives are decoupled, largely decoupled, and in the end it's what we do with the opportunities that present themselves to us. Over lunch I was talking about the importance of having joy in what you're doing. In fact, in the Lausanne lectures, which I often give in Switzerland, I sometimes say to the class, are you having fun? And of course there's a kind of a neutral response to that. It's not exactly a question that you're supposed to answer. But I say, because if you're not, it's not too late to become a dentist. I imagine dentists have fun, I don't know. But don't stick with something because you feel at some point you made a mistake and you should be doing something else. go for a lifetime career, which you feel pretty sure this is the thing I enjoy. I love doing this, you know. And I've been one of those fortunate folks that never had any doubt about it. I always knew what I wanted to do. But I recognize it's very hard for young people today because in the first place, it's a much more complicated world. As far as electronics is concerned, it's a much more highly developed arena of activity. I would say medical electronics is something that's going to be very important. Some new materials to keep an eye on. Not are, but is one material that I'm especially fond of is graphene. I think graphene is going to do big things in the future. Right now, it's a bit like ICs were in late 1950s. You know, the yields were poor. I do remember going to the ISSCC over the years, right from the very beginning. There would be a year when we would hear of a 10-gate logic cell. 10 gates with a single chip. Next year was 100 gates. And on it went, and people were coining terms like small-scale integration, medium-scale MSI, large-scale integration, VLSI, what's beyond that, ULSI. You know, now we've lost track of all that because we're so far away from that trend. But it was funny to go each year and just hear about a decade increase in how many devices or logic gates you can put on a chip. And of course, you know, being this kind of crazy bipolar guy, I would always be thinking, I know how to do that in bipolar. I don't need to do it in MOS. And I still think that, but that's just because we have access to good bipolar processors. I can afford to think that way. Okay, I'm getting a bit croaky. Thanks a lot.